So we talked about our chi-square distribution in our last section and the chi-square test of independence. And so in this section, we're going to talk about the chi-square goodness of fit test. So in a goodness of fit hypothesis test, we are determining whether the data fit a particular distribution or not. For example, suppose a biologist is doing genetic testing and thinks the flower color will appear in a plant species with the following distribution: 25% red, 50% pink, 25% white. The biologist can then collect data on the flowers actually observed to see if they follow this distribution. So in order to perform a goodness of fit test, we need to know the test statistic, the hypotheses, and a few new definitions. So we have our test statistic, right, which we saw in the last section, right, our chi-squared, and we saw this as well, observed, expected, squared, all over observed, expected. Now, where O is the observed data values and E is the expected values, again, if the distribution follows what we expect to be true under the null hypothesis. So for a goodness of fit test, the degrees of freedom are k minus 1, where k represents the number of categories. The total number of observed frequencies is, we say n, right? So however many we've observed total. And the expected frequencies are calculated by multiplying the probability of each entry. So it's n times p. So how the total number and then the probability of that entry. So our null hypothesis is always going to state that the distribution is as expected. And we'll go a little bit more in depth, so if we were talking about the example of the flower color above, we could say something along the lines that we expect the flower color is 25% red, 50% pink, 25% white. The alternative hypothesis is that the distribution is not as expected. Now, just to note, although we are testing the alternative that the distribution is not as expected, this typically ends up being a right tail test due to the properties of the chi-square distribution. And also note, in order to perform a goodness of fit test accurately, the expected value for each cell needs to be at least 5 and a random sample if taken. So we're going to use the TI-84. So it says to run the test on the TI-84, the type the observed frequencies into L1 and the expected frequencies into L2. Then go into stat, move over to test, and choose the chi-squared, so it's GOF for goodness of fit test from the list. If you have an older version of the TI and it does not have this test in the list, please watch the video on Canvas on the workaround. So yes, so some of the older versions does not have the chi-square goodness of fit test. So really just quick, what you want to do is if you go into your stat, we won't really enter any data here, but go to test, and then I'm just going to scroll up. So my calculator has the goodness of fit test, right? So you should see the chi-square test, which we used in the last section. So if you see this chi-square goodness of fit test, then you're good to go. If you do not, then you do want to go to Canvas. You can also probably search on YouTube just a TI-83 goodness of fit test, and it should walk you through sort of the workaround. So it's a little bit more lengthy than if it already had it calculated, but you can still go through and do that, okay? So let's take a look at our first example, right? And so it says a biologist is studying genetics and thinks that the flower color will appear in a plant species with the following distributions. So 25% red, 50% pink, 25% white. Flowers are grown in a controlled environment, and the biologist counts 36 red flowers, 88 pink flowers, and 30 white flowers. At the 5% significance level, does the data suggest the distribution of flower colors differ from what we expect? Okay, so we have, right, 5% level of significance. Our null hypothesis is that the distribution of flower color is, and we just sort of basically say what they told us, 25% red, 50% pink, and 25% white, right? So we just are very specific on what they've told us. Now, an alternative hypothesis, right, we just say the distribution of flower color is not what we expect. So the distribution of flower color is not expected. Okay, so actually, should be not as expected. There we go. Okay. So now I'm ready to fill in the table, right? So it says my observed values, expected, and so observed values, right? This is what I observed. So we said 36 red, 88 pink, and 30 white. We want to get this total here, so let me quit out of my screen. So 36 plus 88 plus 30. So we sample the total of 154, right? So that's basically what n is, so the total. So my expected frequencies is the total times the probability for that. So the probability they said for red, right, was 25%. So we're going to take that 154 times 0.25, and let me actually write that maybe a little smaller so we can write the answer in there. So 154 times 0.25, right? And for pink, it was 50%, so 154 times 0.5, and then 154 times 0.25, right, for the white. So if I do 154 times 0.25, so 38, so, and we'll keep the decimal, so 38.5 are for the red and pink, and then 154 right, times 0.5, that's half of that, so 77. Okay, so that's what I expect. Now I'm ready to do O minus E. So for each of the rows. So observed was 36 minus my expected 38.5. So negative 2.5. I have 88, right? What we observed minus what we expect. And so you can see they can be positive or negative, and that's why the next column they're squared. So I have 30 minus 38.5. And I'm doing each column. You could do each row as well. So minus 8, negative 8.5. So if I have negative 2.5 squared, that leaves me with 6.25. So I'm just going to go through and do that last column. So 6.25, and then we need to divide it by what's expected. So expected, right, divided by 38.5. And so I'm going to do 0.1623. All right, so 11 squared. I'll do the next, right? So I'll do pink. 11 squared divided by its expected, right? 77. So I get 1.5714. I'm just going to 4 decimal places. And my last one, I did not write the 121. There we go. So then I have negative 8.5. And I square that. And then, right, so 72.25. And then I'm going to divide that by my expected, which is 38.5. And so I get 1.8766, right? So the whole idea, right, is to get the sum of this. So we want the sum of the last column. So if I add up these numbers, so 0.1623 plus 1.5714 plus 1.8766, right? I get roughly 3.6103. So what is this value here, right? This is my chi-square test statistic, so 3.6103. Okay. So it's definitely a very drawn out, sort of lengthy process. It's just tedious. It's not too hard, but you can see that if you had, 5 categories or even 6, it can, take a little bit longer. So let's go through and actually do this in our calculator. So what I want to do is I go into my stat button and edit, and I'll clear all of my items in L1 and L2 quick. So I'm going to type for L1, I'm going to do observed, so this will be L1, and L2 will be expected. So I have 36, 88, and 30. And then in the corresponding L2, they're expected. And you'll notice that in the last section, we could just enter the observed. in this section, you do have to calculate the expected and then enter those. So you do have to do a little bit of calculations in this one. That does differ a little bit. And the way that the data is set up, right, the last one, it was a matrix. This is not quite a matrix, right? So we'll quit out of there. I'll hit my stat button, go over to tests. I'm going to go up to the goodness of fit test. Observed, right, expected, degrees of freedom. So how we calculate the degrees of freedom, it is k minus 1, where k is the number of categories. So I have 1, 2, 3, right, 3 different colors. So 3 minus 1, I have 2. So my degrees of freedom are 2, and I can calculate this. And so you'll see, right, that chi-square is what I have here. I have p, right, my p-value, so 0.1644. And if you look at these here, you'll notice that this information here is actually each of the observed minus expected squared divided by expected of each of the colors. So they also do that as well if you needed those. Okay, so I can look, right, so 0.05, right, that's my alpha. 0.1644, this is definitely larger. So we are going to, right, fail to reject and say is not sufficient evidence to conclude that the distribution of flower colors differs from what was expected. So because we're failing to reject, right, basically we're not finding enough evidence to suggest that it does differ, right? There's not sufficient evidence to conclude that the distribution of flower differs from what was expected.